This is Unit 6, Video 11. In this video, we will talk about real gases. Now, we've been talking about ideal gases up till this point, and we've treated all gases the same. In this case, we're going to show that under certain conditions, ideal gases do not behave nicely. They actually change in their pressures and volumes because real gases actually are a little different. So we're going to wrap up this chapter with a discussion of these real gases. And the first concept we'll recall, so the real gases in the real world, the behavior of gases only conforms to the ideal gas equation under mild conditions. By mild conditions, we mean, room temperature conditions are definitely mild conditions. So temperature and pressure should be relatively stable or relatively mild, we'll say. But at high pressures and low temperatures, and really these are the two sets of conditions, high pressures and low temperatures, the behavior of these gas particles then starts deviating from ideal behavior. They stop behaving ideally, and the pressure changes, the volume changes from what you would expect. So this would be an ideal gas, and this would be a real gas. Now, in a real gas, a very, very big difference, and this is probably the most significant difference, is that there are attractive forces between the molecules. In an ideal gas, we assume that there are no attractive forces anywhere between the molecules. In reality, though, there are attractive forces, and these attractive forces will actually usually cause the pressure to go down. And the reason why they'll cause the pressure to go down is because now, if two of these are stuck together, essentially they're behaving as one gas particle. So you've reduced the number of collisions, and therefore you've reduced the pressure. So a pressure decrease will usually be the big indication that you have a real gas. All right. Now, the two assumptions that we'll work with from the kinetic molecular theory, there were four of them, but the two that will be important to us here is the negligible volume of gas particles or molecules. Remember, we said that molecules of gas are so tiny compared to the entire container that you could effectively ignore them. If you collect them all and put them in one corner, they'll just occupy an insignificant amount of space. So we can say that they don't really occupy much space. And then the other assumption was no attractive forces that we just saw above. In reality, there are attractive forces between these particles. They do attract each other. So these break down at high pressures and or at low temperatures again. So high pressures, low temperatures is the way to remember that these two factors break down. Now, the way to maybe remember this is, you know that if you have a gas, oxygen for example, you can liquefy oxygen two ways. You can either lower the temperature, and every substance at a low enough temperature will become a liquid. So that makes sense that oxygen at low temperatures will no longer behave as a gas, it'll be a liquid. But it turns out that you can do the same thing by compressing a gas. And you can actually make gases into liquids by compressing it. We saw this with butane, right? When you compress butane in those little tiny lighters that you see is actually a liquid. And it's a liquid because it's under pressure. So at high pressures, again, you become a liquid. So there's two ways to liquefy a gas: by compressing it or by lowering its temperature. And these are the two conditions at which gases no longer behave like a gas and start behaving like a liquid. So here is the breakdown, specific breakdown, or a little more detailed breakdown. At high pressures, molecules of gas are crowded together, and that's because you have a lot more molecules, and since they're crowded together, the space between them is reduced. So there's not much space between molecules then. The volume of the gas particles then become important compared to the total container. So here is a picture of a bunch of gas particles. There's many more of them than you would expect. So you can't really say that their volume is negligible. You can't say you can't ignore the volume. If you stick them all into a corner, for example, they'll probably take up a good chunk of the corner. And so you cannot ignore their volumes. Their volumes are actually coming into play, which then would allow them to expand. And here it says the gas becomes less compressive at these high pressures, and the volume still decreases, but not perfectly as predicted by PV and RT. So you'll still see if the pressure goes up, we saw that the volume comes down. It's an inverse relationship. So the volume will still come down, but not by much. Say if you double the pressure at that instance, the volume won't get halved. It'll be less than halved, something like that. And we'll see an equation that represents this. The other condition is high temperature. So again, at high temperatures, rather low temperatures, at high temperatures, gas particles behave just fine because they're essentially moving around so quickly that there are no attractive forces between them. If you lower the temperature quite a bit, the molecules now have low kinetic energy. They're traveling slower, quite a bit slower, you can say, and then their attractive forces come into play. It turns out that every particle actually has attractive forces, and we'll review these in the last video. And it's just that they're moving around so quickly that those attractive forces get ignored. But in truth, every particle has an attractive force between them, every substance. And so, but at low temperatures, this definitely comes into play, and the molecules get to stick together. So, if they stick together, then your gas isn't behaving very gas-like. And this also happens at high pressures. So the same idea of gas particles attracting each other happens at high pressure because molecules are very close to one another. So essentially, they have no choice but to attract one another. They're so close. And because there's so many of them at high pressures, they're just a boatload of molecules, because the way to increase the pressure is by just adding more gas, and that's how we do it usually. Okay, so here is the idea. The ideal gas law, PV_nRT, our beloved equation, now gets adjusted by adding two strange parts to it. And these two strange parts, there's something added to the pressure, and there's also something added to the volume, or you can say subtracted from the volume. So our ideal gas law becomes this, and this is called the van der Waals equation. Now, Mr. van der Waal is usually associated with intermolecular forces. So remember, these are the guy that said intermolecular forces like London dispersion forces, dipole-dipole forces, hydrogen bonding. So because Mr. van der Waal realized that gas particles actually have attraction for each other, he came up with this equation, which is pretty neat. And we'll show you how this works. So here's the equation written out, and there are two constants in this equation. And constant A, which is up here, corresponds to the strength of the attractive force between the molecules. So it takes into account the fact that there is an attraction between the molecules. And then this constant B, which is in the volume portion, corresponds to the size of the molecules. So again, because those two assumptions of the kinetic molecular theory are not true for real gases, we have to adjust our pressure and our volume based on that. Now, here it says, when volume is relatively large and moles is relatively small, these corrections actually become negligible, which means if you have a very big volume, then you're technically behaving ideally, more likely. Or if you have a small amount of gas comparatively, you're behaving ideally. The way to get a lot of pressure is just to put a lot of moles in there. So what they're saying is, if this number right here is really, really big, say if it's 10, and this number is really small, say it's 0.1 or something, then really the volume still 10 minus 0.1 is still 10. That's what they're saying. And same thing here. If this is a really big number, 10, then you get to square it. You get 10 squared. That's 100. And then whatever this comes out to be, if this is 0.1, and then divided by 100 is insignificant, no matter what the A is, and your pressure stays the same. And that's what they're trying to say down here. But if your moles is high and your volume is low, then the opposite becomes true. So a tip-off, anytime you have a problem, is that your moles is a high number and your volume is a low number. And that will tell you that you are not behaving ideally. Alright, here is the table for the constants A and B for certain substances. So here's constant A and constant B. You'll notice that for nitrogen and oxygen, they're pretty similar, but then for CO2, the constant is really increased. For water, it's definitely increased. Helium, it's really, really tiny. Helium is actually among the best gases there are out there. It's actually the best gas, so it has the lowest constants for the real gas. And CCl4, this guy is actually a liquid. So at room temperature. Actually, so is water, isn't it? Liquid. But this is much, much higher constants than for anything else. And that's kind of the idea. Alright, so we're going to solve this equation, use this equation to determine and see the difference that really comes out. And that's what this example problem is about. A 4-liter flask contains 4 moles of carbon dioxide at 100 degrees Celsius. Calculate the pressure from the ideal gas law and from the van der Waals equation, and then compare the two. So we've done this from the ideal gas law, which was PV nRT. So if we just plug this in, and we want the pressure, so P in our case would be nRT over V. So let's do it down here. So my pressure, my moles is 4. We got 4.0 moles. My R is 0.08206. And then my temperature, let's get this little T out of the way. My temperature is 100 degrees Celsius, which gives me 373 Kelvin. And then I'm going to divide that by V. That should be a V, apologize. Try to fix it on the fly, and there it is. So we have volume is 4 liters. Alright, so if you calculate this, and I picked the volume and the moles to be the same, so that way they kind of cancel out. So we got 0.08206 times 373. You get yourself 30.6 atmospheres. Now this is under regular conditions. If we now apply the van der Waals equation, we're going to adjust V and P. So I'm going to still put the equation like this, except with the extra parameters. So the van der Waals equation says P, and then P has a term added to it, and the term is plus, I think it said A n squared over V squared. So this will equal to nRT. So we got nRT over V. In this case, V though gets A or B n subtracted, doesn't it? That's right. Okay, so this is what we'll plug in. Now what I'll do is essentially subtract this term on the other side. So because it's added here, if I want to just solve for P, I'll actually subtract it to this side, if that makes sense. So then it'll say this minus A n squared over V squared. So this is my final equation, essentially, that I'm going to be using to solve for P. This equals P. That makes sense. So I simply rearranged it here. Alright, so the nRT is still the same, so we'll put that in as a 4. We got 4.0 times 0.08206. And our temperature is still 373. And then in this case, we have V minus Bn. Now, since we have carbon dioxide gas, we'll have to take a look at the constant for B. Our volume is 4 minus whatever that constant is times the moles. And the moles is also 4. So let's see what that constant is for carbon dioxide. And it is a little messy, but it looks like it's 0.0427. So 0.0427 times 4. 0.0427 times 4. Okay, how about our second constant? We need the constant A from up above for CO2, and that is 3.59. So we got 3.59 times n squared would be 4 squared over V squared would be 4 squared. Same thing here. Okay, so now we have to just do a little more calculation, and let's see. In this case, these two would cancel out just for the sake of ease. And let me see what this is down here. So we got 0.0427 times 4, 0.1708. So 4 minus that gets us 3.829. This is 3.829 at the bottom. And so we get to divide the top by the bottom and subtract 3.59. Let's see what that gives us. So we got 4 times 0.08206 times 373, and then divided by 3.829. Okay, and then we subtract 3.59. And if I did this correctly, which there's a possibility of error, we have 28.4 ATM. Okay, so that looks right because it is close to the ideal gas law equation. but not quite. And actually my pressure went down, which is usually what you'll see happen. You'll see the pressure go down. Now if you take a look, just analyze this real quick. Our original volume was 4 down here from the ideal gas law equation. From the real gas law equation, our volume was 3.829. So notice the volume actually decreased in this case. And then our original pressure was, well, got adjusted essentially by this amount right here, which would make sense. So it makes sense that the pressure changes. Now we do have 2 sig figs, so really it's 28 versus 31, isn't it? So in reality it's 28 versus 31. So by about 2 atmospheres, by about 3 atmospheres, we've adjusted our value. All right, hopefully this makes sense. Just be able to apply this real gas law equation and understand how it works.